So this is the effects of shrinkage and curling on polyester resin laminates when you apply heat to them during the cure cycle. So a quick agenda, it's going to be the introduction and problem statement of what's going on, and then we'll talk about the objectives of the research, followed by the plan for implementing the research. We'll touch base on the experiment design, and then we'll go over the preliminary results, followed by the broader impact of the study, as well as the future considerations and the next steps, really, of the research. So to begin with, there's the shipyard myth that when you cure a polyester resin, and if you add too much heat, it'll actually incredibly increase the shrinkage and curling and spring of the laminate. So the spring being that when you pull the part out of a mold, it curls in on itself. Spring and curling are words used often very interchangeably. It's industry standard to infuse with epoxies based resins and add heat to both speed up the cycle time, increases the transitional glass temperature, and makes everything go faster. But you don't do that on polyesters because of the shipyard myth that it'll increase the spring too much. So the objectives are to either debunk or confirm the shipyard myth that polyester resins will shrink when you apply heat to the curing cycle. But really, with such a vast scope that could encompass, we're focusing on just getting a foot in the door, first look of what actually happens when you add heat during the cure cycle. And so we really want to gather some useful data to get a foot in the door, because that'll kind of determine whether or not this is pursued further, and what avenues to go down. So the research plan would be to build laminates, panels, infuse them with polyester resin, and cure at different ambient temperatures. So what we would do is we would take dry glass, lay it up, bring the ambient temperature to various rates, anywhere between 0 and 90, just because, or I'm sorry, between ambient and 90, just because 90 Celsius is about as the maximum that the polyester resin I'm using will cure effectively. And so we use the vacuum assisted resin transfer method, or VARTM, to infuse it. It's a pretty simple process, but I've linked a YouTube video, as you can see on the slide, that explains it all in depth. Not relevant to the research that I go into it, but it's there for anyone who would want to learn and understand it. So the experiment design, the gist of the work instructions are to lay up 10 plies of unidirectional glass. Unidirectional glass experiences more shrinkage and curling than any other type, so we're going to use that. We're going to lay up 10 plies with all the fibers aligned in the same direction. We're going to add the consumables for the Vartum process, explained on the video on the previous slide. And then we're going to set the temperature to various amounts, 25 Celsius being right about ambient, and then 45, 65, and 90 being the max allowed. Infuse the laminates with the polyester resin, let them cure at their different temperatures, and then we will dissect them perpendicular to the fiber to then lay them on their side and measure the deviation from being flat. So the preliminary results are very interesting. They show like the largest standard deviation from flatness was a millimeter. That meaning that within the different samples, none of them were further than a standard deviation of right around a millimeter different. So that would mean that our gut initial feeling is that these all turned out pretty much the same. The mean of the standard deviations was only a half mil, so everything turned out pretty much the same. There was very little shrinkage, or difference in shrinkage. But the one positive is that as the temperature was raised, there was actually more spring and curling. Very, very minute, but there was a positive correlation, and I'm actually happy with that because it does show that we were able to isolate all the variables, and the only thing that was changing our results was, in fact, the temperature. So the broader impact is we think that from our initial study, there is such little impact on the curling due to heat that should be considered further. What it'll do is it'll reduce the cycle time, because obviously these parts will cure faster. So when you reduce the cycle time, you'll have cheaper components, because less factory time, more per day, more per labor hour. The mold will have higher throughput. It'll be worth its value, so you can get nicer molds faster, throughput of them. But other considerations is now we've opened up Pandora's box and have to think of everything. So polyesters have a very low flash point, so when you add heat, it would be dangerous to reach that flash point, start a fire. Also, the constant heating and cooling of the molds could damage them, and so that could also lead to a rising capex, the higher capital expenditure of the molds, as well as possibly ovens or however you're going to heat them up. So there's the business case there of whether or not you spend more or it's cheaper just to have a lower throughput of the mold.